So let's start with it, and again, some of the marketing, if you wish, I will go faster and spend more time on that technical stuff. What is VMM? Again, it's a framework for doing design verification, implemented in SystemVerilog, mature methodology, because it originally was available as Vera. With Vera, this is called RVM, this was called RVM, reference verification methodology, and that was transitioned from Vera to SystemVerilog as VMM, and maximizes the design quality, emphasizes this is where a lot of people started using it, this form, one verification environment, and then it does. And it does have assertion and coverage, though we don't talk too much about that in the VMM itself, because they are naturally part of it, and this is why I recommend the VMM book, because it has a nice chapter on assertion that talks also about formal verification, what can be done, and etc. And on functional coverage, it talks about what to capture and when to capture and things like that as a guideline. It's very good. So here's the famous VMM picture. Whenever you do Google for VMM or SystemVerilog, it's kind of a picture. You get this, you get the DUT, and very similar to how we had layers in VM. It's the same in VMM. We have driver layer and or the common transactors, as we call it. Then there are optional functional transactors. Then there is generator layer, the configuration, and the test case. This whole thing is called the ENV, the bottom box, and this top is called multiple tests that can come in. Okay. So this is the operational domain, this is the analysis domain. If you want to combine, now we have updated it to parking in OBM/UVM as well. This is the operational domain, this is the analysis domain. So one slide on what each component does. You can read it in detail. This is the DUT, and this is where the interfaces come in. Then this is the driver DF that drives the DUT, as we were talking yesterday. And then this is the one that could translate higher level transactions into lower level transactions. Then we have generator on top, and then the configuration of the test bench and the test cases. And on this side, you have the monitor that absorbs the data from the DUT. It identifies the transactions. Let's say you want to do fragmented packets. Where on the output side, you get multiple packets. You defragment them, that is, collate them, and then publish it to the output. Then the coverage. So quick look on these individual layers. Signal layer, it's not limited to IO signals. Remember, you can always go down using the internal signals, the dot operators, and you can bind assertions to internal signals. So assertions become part of this layer in a sense. Command layer is where we are right now. The traditional bus functional models become part of this layer. Execution of bus interface tasks like bus read, packet transmit, fetch instruction, collision, etc. And it's essentially, it does one transaction at a time. That's what we call as atomic physical layer transactions. Now, on the functional layer, it translates transactions into atomic commands or atomic transactions. For instance, you could translate a bus read into multiple read commands. You could take USB transactions into small packets, TX and RX. You could take video frame into sinks, lines, and pixels, so on and so forth. For smaller designs, this may not be visible, but larger designs it is. It translates on the other side, observed commands into transactions, write commands into write bus. If you look at this side, that's how it is. Okay. Scenario layer, if you had directed tests, you don't need them, but if you wanted random tests, then you have what is called a generator layer. From there, you generate stream of transactions, could be atomic, could be sequence or scenario generation, and this could also, atomic transactions could also influence your test configurations, and fairly uncorrelated data in terms of just random transactions, as many as you want. And this could be, the scenarios could be back-to-back transactions to the same address, loop structure, high density data burst, and etc. So fundamentally, this was differentiated in VMM to say that there is an atomic generation, then there is scenario generation, And the way scenario generation was implemented and was working was to with array-based randomization, which is even today is little unstable, undefined, let me put it this way, or at least from a developer to user perspective. Users have a view that yes, it should do out of the box in the tool. The tool will just come back and say, no, that's not possible because of XYZ reasons. In SystemVerilog, you can't have an array of classes and be randomized in one shot. Fine, but that's what we need. So how do we do it? So there are workarounds done inside the scenario library. If you are interested, I highly recommend to look at it. The scenario generator, it's something yesterday we were talking, 2 days back when we were talking. The array-based randomization is completely done inside this base class, if you are interested. I'm sure it's natural way of doing it, but it just means that it's doable, but it takes time and it takes its efforts and etc. Arguably, this was a better way to do scenario randomization, but tools had enough of time. So, and in parallel, there was EMERN, and from where the OBM emerged, and there the scenario was directed differently. It put the onus on the user to say, I give you a body, you go and describe the scenario more procedurally. That's a procedural way of randomization. Here, more declarative way of randomization. And according to some experts, declarative way is far better in terms of state space coverage and etc. So, but we have seen that it could take enough memory and etc. out of the tool. So it's a choice that user could make. But fundamentally, the scenario generation, regardless of how it is implemented in the base class versus the tool, this is needed for the design verification, because there are some classes of parts that I will find only if I do scenarios. Simplest example could be a memory. If there is a memory that you want to, that you can do read and write. At the end of the day, you must write, then read back. Maybe in some random order, but you must read back the addresses that you wrote. Otherwise, you are not doing a fair bit of testing. You can do totally random 1,000 transactions that could have done, let's say, equally 500 reads and 500 writes. But if there was no correlation between what address you wrote and to where from you read, the kind of verification you did is not so useful from an application perspective. It's still useful. In verification, all of things are useful. It is good. But the so-called meaningful application level test could not be written just with random others, atomic transactions alone. Scenario generation is by far needed. It's a fundamental requirement in verification. So this is a must to have. How we implement it, that's up to us. Coming to the test layer, basically, if you had done a test, this could sit on top of transactor, this functional transactor layer, and it could involve manual creation of transaction streams. This is, in a sense, what we showed even in the past with the UVM lab. The very first lab, we said, okay, you will reset, send one transaction, come out. And you could use still a little bit random data filling, usually run model 1 because it's a random test. Constraint random test, it is used on top of scenario or the generator layer. It uses or exploits the constraint random generation, constraints, distributions, new scenarios, and it's always recommended to have one test run with multiple seeds. And this is why I keep insisting the seed generation must happen with a little less performance overhead. Call it compile time, call it lab time, call it runtime, that's up to the tool. From a user perspective, I want to launch the same test with different seeds. It's a very fundamental requirement in constraint random simulation. Very, very important. And as little performance overhead you add between one run and another run with different seed is very good for the user. So in terms of how it supports, it's in terms of communication, there is intercomponent communication. The generators, you have atomic, scenario, and custom generators that you can build. And the control flow of the environment, so-called phasing that we keep talking about, I'll explain how it works. It was very well thought out and done. And reuse and extendability in terms of callbacks and factory pattern. The factory pattern, admittedly, was not as sophisticated as an OVM/UVM, But VMM 1.2, remember this is all about VMM 1.1, 1.0, rather 1.0 and then 1.1. 1.2 added these facilities, advanced factories. But that's not very well used today, VMM 1.2. Don't know if you even compare 1.2 to you. 1.2, I would say, if you don't, we don't see a lot of users. There are some, not very many users. And even though it's called 1.2, it's really a 2.0. It's really a big change. It's more to do with the marketing and the way you position things. But 1.2 is not a minor update. VMM 1.1 is okay. VMM 1.2, in terms of number of users, when they look at it, they realize, okay, instead of moving to 1.2, I would rather move to UVM. This is usually the idea of UVM or UVM. So, again, your data could vary, your marketing and others. I can tell you something else, but this is what we see. And logging of results, again, like a report info, but we did it differently using VMM log. And the style is in creation of test benches, we have successful OOP design patterns, the guidelines for reuse and use of the circuit. And sitting today, looking at VMM, looks probably, oh, these are naturally done in UVM. What's the big deal? Or people do understand. But remember the time we kind of invented and deployed VMM, this was very hard sell. Because people said, oh, I can do this in Verilog, I can do this in brain system Verilog, why do I need VMM? So some of this material is fairly basic with respect to UVM, but you would see that it was all, this was the beginning of all these technologies. Right? It's a very interesting approach to this. So, virtual interface channels, this we call a T that you could do on channel. One channel could give multiple copies, and the broadcaster, scheduler, there is a sequence that will talk about this notification. It's an event-based mechanism, but a little more complex and more robust than the events, where the system will log events and then complex. And that's another quick note on VMM usage for customers.